Okay. Hello, everyone. Welcome to this candidate talk by Cameron Muskill. So Cameron is currently a grad student from MIT, supervised by Nancy Lynch. He works on large-scale algorithms across a number of fields, ranging from like numerical linear algebra, such as for like Lando's method for PCA, such as like low-rank approximation and so on. And also he has worked on sublinear time algorithms for low-rank approximations and so on. And he recently also started to work on social network algorithms, and as he also has interest in biological computations and so on. So this talk is about the power of simple algorithms from data science to biological systems.
All right, thanks. Okay, yeah, so today I'm going to be talking about the role of simple algorithms in data science. Specifically, I'm going to talk about why really simple, often randomized methods like stochastic gradient descent and random hashing and random sampling are so powerful and so ubiquitous in data applications. And I'm going to overview some of my work in this area. So specifically, I'm going to overview some work on a new class of sampling algorithms for linear algebraic computation that let us do some really powerful and surprising things. Like, for example, sublinear time low-rank approximation for certain matrices and some really nice things.
Sorry, can you speak up a little bit?
Yeah, sure. So I'm going to overview my work on sort of investigating these algorithms and especially their role in linear algebraic computation. And then if I have some time at the end, I'm going to talk about some connections with biological systems and trying to understand when we're studying really simple randomized algorithms, really it's all about figuring out how small stochastic interactions can lead to some sort of complex behavior. And I'm going to talk about how insights from this can be used to study beyond algorithm design, but algorithms that are being conducted in nature, and specifically some decision-making algorithms that ants use. All right. So we all know that data science and machine learning are huge consumers of algorithms. And we also know that algorithms aren't just a nice to have. Fast algorithms aren't just saving us resources. They can really lead to breakthroughs in these areas. The thing that's probably at the forefront of a lot of people's minds, for example, is the success of deep learning and neural nets for image classification. This has been driven forward by a lot of many advances, one of them being that we can just scale these networks to huge data sets and also just to huge model sizes. So that's really a computational breakthrough that's driving a learning breakthrough. In genomics, the same thing's happening. Basically, we can do genetic sequencing way faster than we could do before, and this is a computational breakthrough. Basically, we're able to take a bunch of short reads of DNA and stitch them together massively in parallel, and therefore generate more data for ourselves and actually generate the ability to get insights from this data. So these are just some examples. Another one is like in remote sensing, the ability to do real-time hazard monitoring. This has been driven by computational advances. So computational advances matter not just for saving resources, but really to drive breakthroughs in learning and science. So what do we need from algorithms? If we want to design algorithms that help push these advances and actually like push forward science and learning, what do we actually need from these algorithms? The first thing is sort of a given. It's just, if you're an algorithm designer like me, this is what you're always looking for. You want fast algorithms. And if you're going to run them on big data sets, you want things that run, say, in linear time and are just extremely fast and easy to implement. But the other thing is a little bit less defined. We somehow want the algorithms that are going to actually have impact on practice are algorithms that are somehow flexible and simple. They're things that we can adapt to like a wide range of application domains. They work well on lots of different input types. They work well when you tweak the problem that you're trying to solve a little bit or tweak the model that you're trying to train a little bit. And they also work well in lots of computational environments, and they're easy to implement in lots of computational environments. So a lot of computational advances aren't driven necessarily by algorithm design, but by system design, and we want our algorithms to fit in with this. We want things that it's not hard. If there's a new distributed system that's become popular, it should be easy to adapt the algorithm to the system. It should be easy for people to implement and test and actually bring up to speed. And so sort of the thesis of this talk and of a lot of my research is that really simple randomized methods often satisfy these criteria that we're looking for of being simultaneously really fast, but also being easy to implement, flexible, robust, and all these types of things. So I'll just give you a couple of examples of sort of really common randomized algorithms that are used in machine learning and data science. Probably the most well-known one is stochastic gradient descent. Gradient descent is already pretty simple. I'm trying to optimize a function. In every step, I walk in the direction of steepest descent, and I eventually converge towards a minimum or a local minimum. In stochastic gradient descent, I just say, I don't want to compute a full gradient. Maybe I just want to look at one data point at a time and compute a gradient based off that, some really coarse estimate of the gradient. which is correct in expectation. So I have this gradient tilde, which is correct in expectation, but might be really far off, and it might not really correlate that strongly with the gradient. I can still take small enough steps in these directions and eventually find that I converge to a minimum. And this is a hugely applied algorithm. Why is it so popular? One, it's applicable to a really wide range of problems, just like gradient descent is. You can sort of throw it at any optimization problem you had and see what happens. It's really naturally distributed. It's naturally streaming. The steps that you take are really cheap. And this is a really nice thing in practice. You don't have these big expensive steps. You have really cheap many steps going on at once. And we also have some theoretical understanding of it. At least for convex functions, we don't understand exactly why it works for all functions we apply it to. But because it's simple enough, we can really do some analysis on it and try to use this analysis to understand what it's doing, to understand how we'd like to modify it and improve it and things like that. Another example are Markov chain Monte Carlo methods. They're sort of like stochastic gradient descent, in that you can throw them at tons of problems and see what happens. They take really simple steps. I'm trying to sample from a distribution. I just need to say compute ratios against this distribution and take relatively simple steps. And they're easy to implement. It's not, if I want to implement one of these methods in a number of systems, it's easy to do. And then my final example, which is quite close to my own research, is random hashing and random feature hashing and random projection. Basically, this is I have like a large data set for whatever reason. I have many data points I have many features. And I randomly compress this data set using some sort of random hash. So what I mean is literally I randomly take features or I randomly take examples and I add them together, maybe with some appropriate weight function. Another way of viewing this is I generate some random matrix pi from some distribution, and I compress my matrix with it. I take A and I multiply it by pi and apply this random linear compression. And I hope that I get something useful out. I hope that this compression A tilde I can then use in downstream applications for things like clustering or PCA and things like this. Again, this method applies to a huge range of problems. It's sort of a very generic pre-processing method, almost like PCA in a way, where you can apply it, you can shrink the size of your data, and then you can see what happens to your results. It's naturally distributed. It's based on basically just doing matrix multiplication, which is a super easy thing to implement and is widely implemented, basically implemented in any system that you're going to be using. And again, because it's simple, I mean, it takes some math, but we have good theoretical bounds for it, and we have some good theoretical understanding of it. Based on sort of Johnson-Lindenstrauss type results and random matrix theory, we can actually sort of figure out what it's doing and why it might be working well. Okay, so also mention that all of these algorithms I mentioned and other randomized algorithms, these simple randomized algorithms, come with other advantages. They take small local steps often. This is certainly true of stochastic gradient methods. And this makes them sort of more tolerant to noise and perturbations. For example, there's a lot of work on stochastic gradient descent in asynchronous systems, and where you basically get perturbed behavior because you don't synchronize the processors running the steps very well, and you still see good behavior in these systems. So these algorithms can be perturbed and seem to still work well. They all aggressively trade approximation for efficiency. So all the ones that I mentioned are approximation algorithms. Randomization and sampling and sketching naturally lead to approximation algorithms. And the good thing is that often in data applications, there's not some canonical answer we're looking for. We have noise over the data anyways, and by allowing ourselves some approximation, we can get much more efficient algorithms. And then something that I mentioned while I was talking about these is a lot of these have relatively clean mathematical analysis as basically probabilistic processes. With random sketching, yes, it's an algorithm, but what you're really doing is you're saying, I have a random matrix that I generated. I applied this to my data set. What's the effect of this random linear map on my data set? And so it's a rather simple thing to sort of try to pin down and figure out what it's doing. Okay. So this has been the goal of a lot of my work, is to basically build out the toolkit of these simple and general purpose randomized methods for data problems, and also our ability to understand exactly what they're doing and to analyze them. And my work, as Zaewon mentioned, touches tools in theoretical computer science, also in more traditional numerical computation and optimization fields. So one thing I've been interested in, especially interested in, is, for example, stochastic gradient methods, which I talked about before. I've been interested in understanding how these methods can be applied to linear problems, canonical problems in linear algebra, which are useful for data science. So one thing I've a lot of times we have bounds for stochastic gradient methods for convex problems, things like solving linear systems, but we don't necessarily have bounds for other problems, for non-convex problems. And what I've looked at is combining these methods with tools from numerical linear algebra like Krylov subspace methods, and using these to sort of boost the power of these algorithms to try to solve things like eigenvector approximation, spectrum approximation, certain forms of regularized regression, to try to expand their use in linear algebra and in data science. And this has required turning back to these older tools like Krylov subspace methods and understanding how do they play with noise and approximation, how are they robust to this noise. Another piece of my work is understanding random sketching methods for linear algebraic graph problems and data problems like clustering and low rank approximation. And a theme of my work here has been trying to understand, given a random projection method or a random hashing method, how do I really characterize? I'm taking my matrix and I'm randomly compressing it, and then I'm going to do an operation on it. What is the right way to characterize what the compression does to my matrix and how it approximates the original data? And then if I can characterize this in a really nice, clean way, then I can use this to give applications to lots of downstream problems. So this has been a focus of my work there. And then a huge amount of my work has been on sampling. And sampling is mostly what I'm going to talk about today. Basically trying to figure out what is the right way to sample for linear algebraic and data problems. And what I'm going to focus on today is a line of work which focuses specifically on importance sampling methods in graph algorithms and linear algebraic algorithms, and sort of a new class of methods which don't fall into the range of stochastic iterative methods. They're not quite the same as random sketching, although there's certain similarities. And they allow us to do some really powerful things for canonical problems like low rank approximation or linear system solves. And then, if I have time, I'll touch back on this connection to biological computation and some work that I've done on stochastic decision making in ant colonies, and how we can analyze this behavior using a distributed algorithmic perspective and using a lot of the same tools we use to analyze the algorithms that we ourselves design. Okay. Let me just briefly overview. So as you noticed in this last slide, a lot of my work is on computational linear algebra, and specifically on computational linear algebra focused on data problems. So let me just briefly overview the role of computational linear algebra in data science and why I think it's such an important area of algorithms to be looking at. Basically, data is often represented as high-dimensional real-valued vectors. And when this is the case, you can represent your data set as a real-valued matrix, with n rows representing the data points and d columns representing the features. And then transformations on this data naturally become linear algebraic operations. So things like principal component analysis, spectral methods, nonlinear dimensionality reduction, kernel methods, linear models, these things are all really bread and butter linear algebraic operations that we run daily on data problems. And they really come down to figuring out how to do basic linear algebraic computation faster. The paradigm of working with data through matrices and through linear algebra is so prevalent that often we have data that we can't quite represent in this form, and we actually try to transform it. So things like word embeddings and word2vec, or spectral embeddings for graphs and things like deep walk. This is such a powerful computational paradigm that we often try to fit things into it even when they don't seem to fit in initially. And this is because we have a lot of really powerful computational tools in linear algebra that we can use to our advantage for processing data. Okay. And many applications of linear algebra boil down to two core problems. There's the really core problems like multiplying matrices together, multiplying matrices with vectors. But then beyond those, there's sort of two really core problems at the heart of a lot of what we do. And these are the problems I've sort of focused on in my research. One of these is solving linear systems. So solving linear systems, you might think of as applying the inverse of a matrix to a vector. Another way to think about this is you're just trying to solve this minimization problem. I'm given a matrix A, I'm given a target vector B, and I'm trying to find a vector X that minimizes the difference between AX and B. It's like ordinary least squares regression. It's used as an internal loop in things like iteratively related least squares for generalized linear models. It's used inside of interior point methods. And also, it's equivalent to like a projection problem. The columns of A sort of define a subspace, the column span of A. AX is some vector in that subspace. And what we're looking for when we solve this problem is we're looking for the vector AX, the vector in that subspace, which is closest to our input vector B. So this is a really basic, if you're working in Euclidean space and you're working in sort of with vectorized data, this is a really basic operation that you need to have. You're figuring out how close a vector is to a given subspace. And then the other problem that I've focused a lot on are computing the top singular vectors of a matrix or computing the top eigenvectors of a matrix. Basically, you want to find the singular vectors which correspond to the largest singular values in a matrix, or how this is often viewed at a high level is you're trying to find the directions of greatest variance in your data. And the reason you want to do this is usually you end up at some point you end up projecting to those directions. Basically, you end up approximating your data set by just looking at the directions of greatest variance. This is the basis behind PCA, spectral methods, and nonlinear dimensionality reduction. One way that I like to view this problem is we don't actually care about finding the well, sometimes we do, but we don't always care about finding the directions of largest variance. We don't actually care about finding V1 through VK exactly. What we often care about is just that we capture most of the variance overall. So what we do is we use these directions to generate something like a low rank approximation. So specifically, if I let V be the matrix whose columns are my top k singular vectors, those are the directions of greatest variance in my data. If I project my matrix to them, so I form this matrix AV V transpose. I've drawn this out here. This is like a thin matrix AV times a wide matrix V transpose. This is the minimum. This is the rank K matrix, which is closest to my matrix in a bunch of norms, for example, the Frobenius norm, where I'm just adding up the sum of squared entries. Now, this is really oftentimes why you want to use computing the top k singular vectors, because we find that in practice, a lot of matrices are close to low rank, or at least they have decaying spectrums, and you can approximate them reasonably well by low rank matrices. And so this is exactly why you compute these singular vectors. You project to them so that you can approximate your matrix as well as possible with a really concise low rank representation. Another way of thinking about this is you just find a projection of your data that preserves as much structure as possible. Basically by hoping that by getting a matrix as close as possible to your original matrix, you preserve as much structure as you can. So that's how I'm going to think about this problem. I'm not going to focus on these singular vectors themselves. I'm going to focus on sort of the main reason we care about these singular vectors, which is computing low rank approximation. Okay, so how do we solve these problems? These are these two problems, linear systems and top singular vectors. They're sort of actually very closely tied together how we solve these problems. They're sort of the textbook direct methods, like things you would learn about like Gaussian elimination or Strzelecki decomposition. There's a lot of work in this area. These things take a long time. For an n by n matrix, they take n cubed time. So you can't run these things on large matrices. They are really important algorithms because you often run them as sort of subroutines on smaller matrix. All of my algorithms will use these sort of direct methods as subroutines, but we'll run them as small samples of our original matrix. But you can't just go and run them on a large matrix. It's just not possible. Iterative methods are things like conjugate gradient for linear system, Lanczos methods, gradient descent for linear systems. These things basically, their basic operation is doing a matrix vector multiply, and they use some iterative approach to try to get closer to the solution to a linear system or solution to some eigenvectors, with each iteration being a matrix vector multiply. These things are generally much more efficient than direct methods. You can actually run them on large matrices. You can distribute your matrix vector multiplies. But again, every multiplication that you perform is doing a full pass over your data. So there's still a question of, is this really the best we can do? Or do we really need to make a full pass over the data for every single iteration? And so my work sort of falls in a third category of algorithms, which has only sort of recently recently grown up in some way. The methods here are randomized. So things like compressing your matrix with random hashing or random projection, stochastic gradient descent, what I mentioned, and random sampling, which I'm going to talk about in this talk. These things are trying to sort of access your matrix in a very local or limited way, not do a full pass over your matrix for every iteration, and they're trying to exploit this to get faster runtimes. You can often get really fast, surprisingly fast runtimes. Like one thing you see sometimes quoted is you can get runtimes of the form NNZA, so that's the number of non-zeros in your matrix. So if I stored my matrix as a sparse matrix, this would be the time it takes me to read my matrix, just the list of entries. Plus some lower order terms, like depending on lower dimensional terms. So for low rank approximation, for example, you can get runtimes of the form order NNZA, basically order 1 reads of my matrix, plus some term which depends polynomial on D, the dimension, and K, the rank of the approximation that you're doing. And so these can be a lot faster than iterative methods, which require many applications of matrix multiplication, many things that cost NNZA if you're doing sparse matrix multiplication. And as I said, they typically access the matrix in a very limited or local way. So that's what I'm going to be talking about today. And specifically, I'm going to talk about sort of the simplest way you could imagine to speed up matrix computations, which is random subsampling. You give me some large matrix. I can't afford to run a direct method on it. I can't afford to run an iterative method on it. What I'm going to do is I'm just going to subsample it down. I'm going to select uniformly some subset of the rows, which correspond to data points, or I'll select some set of the features, and I'll hope for the best.
So just out of curiosity, so these iterative methods which require times number of iterations, like you said. So in typical applications for like typical, I don't know, problems, what should I think T to be? Is it like hundreds or 3?
It sort of depends. It shouldn't be like 3, but it's probably dozens or maybe hundreds. I mean, it sort of depends. People use these methods on problems that they can solve with these methods. So in the case that you can actually solve the problem well, it's maybe dozens or something like this, like on reasonably well-conditioned matrix.
Compared to NZ bound.
Yeah, it sort of depends, I guess, what the constant factors in that NZ bound are. I mean, so iterative methods, yeah, I don't mean to trash on them. They're still like a very active area of research, and they're like, I think that there's a lot of work on iterative methods in numerical computation community that like could be used in data.
Computing people use.
Yeah, they use these things. Yeah. So yeah.
Depend on the accuracy you want, or?
Yeah, usually. So the number of iterations depends on the accuracy, though. Usually, though, the iterative methods are much more accurate in some sense than these randomized methods. So usually, you can, if you make some assumptions, you can get like linear convergence. Whereas these randomized methods, usually you're taking samples and you get some sort of like worse convergence. You need to take more samples to get higher accuracy. Yeah. These things also play really nicely together. So this is one reason, I mean, you can often use randomized methods to accelerate iterative methods, like randomized preconditioning. You can combine stochastic gradient methods with them, so they play nicely together. Yeah. All right. Yeah, so random subsampling. This is what I do if I don't know what to do. I could just subsample my matrix down, and then I could hope that working on the subsampled matrix seems to work well. And this is used all the time. So if you have, this is used all the time, for example, in exploratory data analysis. I want to test out if a model works. I just subsample my data points. I run it on a much smaller set of them and just see what happens. It's also used with feature sampling. So for example, in genomics, they have more intelligent ways of selecting features, but there's always some massive feature selection process first, or often some massive feature selection process first, before any real analysis, any further analysis happens. So this is a really prevalent method. The problem is that if you're just doing uniform sampling, this is really cheap, but it's also wasteful. In a way, as you can see, you're just throwing out information. You're throwing out data points, or you're throwing out features. And often the sample doesn't well represent your matrix. So a simple way to see this is if I have a clustered data set, say with some imbalance in my clusters. I might not know these clusters, but sort of my data falls into these 3 clusters, and one of them is a lot bigger than the other ones. Then if I do uniform sampling, I'm going to tend to get more points in that cluster, and I can easily miss like all the points in this 3rd cluster. And for all I know, those are the points that really matter. Maybe those are the features that really contain a lot of my noise. So uniform sampling can be problematic. And for this reason, there's tons of work on figuring out, well, what should we do instead of uniform sampling? There's sort of clustering and distance-based methods. If you've heard of them, there are these things called determinantal point processes, which are a really nice way of formalizing, selecting diverse sets of points or features. There's classification-based methods where you sort of run classification using small subsets of the features and use this. So there's lots of things that have been studied here. For example, with this problem, the solution really wouldn't, this case, the solution wouldn't be super hard. I could cluster my data first. I could explicitly identify these clusters. And then I could like rebalance my sampling to try to get enough points in this cluster. So this would sort of overcome the issue with uniform sampling. So these non-uniform sampling approaches, these sort of important sampling approaches, often work really well in practice. But the issue is that it's really hard to define exactly what makes a good sampling scheme. We can run a sampling scheme, we can see what we get as far as classification accuracy or some downstream thing, and we can declare that it's good for that problem. But it makes it sort of hard to develop sort of generic methods, like I was saying at the beginning of this talk, that are based on sampling. It makes it difficult to understand, well, how can we get these to work for many problems at once? And how can we prove that this is the case? So in a sense, they're sort of inherently heuristic or ad hoc, because we don't have before we have a good definition of what a good sampling is. Okay, so that's sort of the goal of my work on sampling, which is basically to understand what is the right way to select data points or features for generic linear algebraic computation to do fast approximate linear algebraic computation. And this is obviously an interesting question for all sorts of algorithms in learning, in optimization. I'm focusing specifically here on linear algebra. I want some generic sampling method that lets me speed up like solving linear systems, low rank approximation, and a lot of the standards of those computational tools. Okay, so the first step is that in designing such a sampling scheme is we're going to restrict the types of schemes we consider. Specifically, we're going to only look at schemes which are relatively simple random processes. I'm only going to look at sampling schemes that look like this. I assign some sort of score, some probability between 0 and 1 for every row in my matrix. This represents the sort of importance of that point in composing my matrix or my data set, which I'll explain how we compute these later. And then what I do is for every point, I just sample it independently at random with probability pi. And so it means that once I have this importance sampling distribution set, my sampling process is super easy. It's just flipping a bunch of biased coins, and this gives me my sample from my matrix. And then I'm going to hope that this sample somehow well represents my original data in some metric. And we're going to analyze the effects of the sampling. I'm not going to get into this at all during this talk, but we're going to analyze this as a random process. We'll review selecting these points as basically choosing a random sampling matrix and applying it to our matrix, where it just selects out individual rows of the matrix. This is like it's not a huge technical innovation or anything like this, but doing random sampling makes analysis way easier than, for example, we could have computed all these scores and then just selected the points with the highest scores or something like this. But these things become really difficult to analyze. Here we just have a really simple independent sampling process, and that's how we're gonna try to approximate our matrix. Okay, so then the question becomes, how do we compute these probabilities pi? So naturally you think, well, it depends on the problem I'm trying to solve. So for linear systems, I'm trying to solve this problem, minimize ax minus b. What I might want is that after I sample my matrix, so I instead solve the problem on, is this thing working? I instead solve the problem on SA, the sampled version of the matrix, and SB, the sampled version of the output vector. I might want this to give me a reasonably good solution. Maybe it's a near minimum for my original problem. So this is, I would try to look for sampling probabilities that guarantee that this is going to happen with good probability. For low rank approximation, I might ask a different thing. I want to sample my matrix. So I have this matrix SA, my sampled matrix. It's going to be much smaller than my original matrix. I want to compute its top singular vectors. And then I want to project onto them, compute this AVS VS transpose. This is a low rank matrix. If VS has k columns, this is a k rank matrix. I want this to be a near optimal low rank approximation. If I look at all rank k matrices, this one's nearly as close as possible to my original matrix. So this is a sort of optimization viewpoint of how can I solve this problem approximately well. The problem is that if we start going through all these various problems, it seems like we're going to require different sampling distributions and a sort of different analysis for every single problem that we're trying to solve. And this isn't what I want. I want something that's very general. Just like you can do very general analysis of things like stochastic gradient descent, I want something that applies to a huge range of problems at once. So you can just take the same problem, the same algorithm, and apply it to a bunch of different problems. And the key idea here is also pretty simple, but it's pretty powerful, is that instead of looking at problem-specific guarantees, I want to approximate this problem like nearly optimally, we're going to look at really simple spectral approximation guarantees. What this means is I'm going to ask for any vector x, I'm going to want to preserve the product with my matrix. I'm going to want to preserve the product a times x. So specifically, if I look at the product with my sampled matrix, I want this norm to be close to the norm of the product with the original matrix. And I'm going to allow myself two types of error. I'm going to have this epsilon multiplicative error, so it's close multiplicatively. And then I'm going to allow myself some additive error in terms of this lambda parameter, which says even if, for example, ax was 0, I'm going to have still maybe I might not get exactly 0 out when I multiply by sax. This is like a really simple linear algebraic guarantee. It's just saying how close A and SA are when they act as linear operators. So I'm basically saying I'm applying these matrices to vectors, and I want to make sure that they're doing pretty similar things. And the nice thing is that this sort of guarantee, it's easy to write down, and you can then start playing around with this guarantee, and you can show that it can be used if SA satisfies this guarantee. For example, if it satisfies this guarantee with lambda equals 0, you can use it to get epsilon approximate linear system solvers, or preconditioners for iterative system methods. if you increase lambda to the appropriate value, you can use this to get near optimal low rank approximation algorithms. You can use it to get approximation algorithms for constrained optimization, things like non-negative PCA and k-means clustering. And this has been a lot of, it's sort of a simple, it seems simple, right? Map this guarantee to all of these problems. It's not necessarily that simple, and you have to, it's not necessarily always as simple as it looks. And a lot of my work has been focusing on what's the right way to map this guarantee to giving approximation bounds for all of these problems. Okay.
This seems to be a harder condition than solving those two specific problems, right?
Yeah.
Maybe the algorithm is more generic, but
yeah,
maybe
so
it
does seem to be a harder condition, but sort of in the end, for example, for linear systems, yeah, in the end, it seems to turn out that the results we can get match what people were getting if they just targeted those specific guarantees. And we often get guarantees that it would be so.
Imagine for the two problems you mentioned, but this seems to be the.
Oh yeah, that's true. This isn't. Yeah, there's certain problems where this is definitely not necessary. Yeah, for the two problems I mentioned, this is almost like tight in a way. Like you better be getting this. Yeah.
Basically, this is the operation.
Yeah, well, because this is sort of preserving the spectrum of your matrix. But yeah, you're right. For some problems, this might be overkill. Yeah. Yeah.
I guess I'm kind of surprised that what you want is to preserve the norms. I would have thought it'd be something like the difference between the two projections instead of that you want their norms to be similar length. That seems,
yeah, so if you just preserve the distance, you mean the difference between the two subspaces spanned by these?
Like some term about like SAX minus AX, and then something about like that being, not too large on average or something.
Yeah, I mean, so yeah, it's a little bit hard. So SAX and AX are like different size things. So you have to have like a certain right way of defining this. But for example, this means like I preserve distances between, if I'm looking at AX minus AY, I'm also this is gonna be approximated by SAX minus SAY.
The norm will be, this will approximate the norm properly, not the actual like
the norm,
direction.
Not the actual direction, yeah.
Yeah.
But generally, yeah, it won't approximate the actual direction. Yeah. It's a little hard to say what it means to approximate the direct. Yeah, it sort of depends. I mean, yeah. SAX and AX live in different spaces, so it's a little hard to define that, yeah.
I see.
Yeah.
Yeah.
Yeah. Okay.
And this is also the worst case for every vector.
This is also for every vector, which is certainly not necessary. I mean, often this is what we want, but this is not necessarily all the time. And for example, like Johnson-Lindenstrauss type results are doing this not for every vector, and they can often do something much more efficient. They only care about, say I have a bunch of vectors I'm trying to compute closest distances. I only care about preserving this for all those vectors in my data set, not for every possible vector.
So intuitively, if you have a data point repeated like 10 times, this presumably is going to drop 9 of these occurrences,
right.
Keep only 1.
Right.
So can you explain why this does that?
So if I literally have 10 exact repeats of my data points, and if I knew that I had 10 exact repeats, it's going to drop all but 1. And also S is going to be, I guess I didn't mention this, but S is also going to reweight data points. It reweights by the inverse of the probability I selected them. So if I literally like exactly knew I selected them with probability 1/10, it will reweight them up by 1 over that probability by a 10 factor. So actually what I'll do is I'll exactly preserve the norm. I basically compress those all into one row of my matrix. So this is when it works like really well, yeah. And if I have a bunch of, for example, really small data, say I have a bunch of data points that, or I don't know if we should be thinking about these. It's hard to just call them data. Say I have a bunch of rows in my matrix that are really small. They have very small norm. They will tend to have very small dot product with my vectors x. And those might, for example, just be dropped altogether. In that case, might go into this additive error term, this lambda x. Okay. Any other questions on this? Yeah.
So matrices S that correspond to sampling points independent of probability pi, they have some very special, it's like, what is it? Is it like one non-zero per column or something like that?
Yeah, they're actually, yeah, they have like one non-zero per column. Yeah, and that's it. But what I sort of like to think about S as, okay, computationally what it is what it really is it's a matrix, it's an identity matrix, where you just deleted almost all the columns, and so therefore you're only selecting like some subset of them. Yeah.
And you can do this on both ends, right? You could be doing it on the feature space as well instead.
Yeah, actually like for lowering approximation, this is actually like what you're more typically doing. I was just throwing it on, Yeah, it doesn't matter what way the directions are going. All of our bounds, they'll be for either sampling data points or for sampling features, yeah. Sometimes it's more interpretable for sampling features, in my opinion, actually. Okay. All right. So, okay, we have this bound. This is the bound that we're going to target. It's this very simple spectral bound. This bound has been studied in a lot of different contexts. And it's sort of known how to derive good sampling probabilities in order to obtain this bound with good probability. So there's been some work in matrix approximation literature, also in spectral graph theory, algebraic graph theory, trying to get these sorts of bounds. Not necessarily all of these works give actually slightly different formulations, but what I'm going to show you right now is like the sort of cleanest formulation that we've come up with, which is this thing called a ridge leverage score. This is what I'm going to define my sampling probability to be. The actual form of this doesn't matter too much. The point is it's some score. It's the probability that I'm going to sample the ith row of my matrix. It depends on that row. It depends on the matrix. It also depends on this lambda, this additive error that I'm going to allow myself. It's basically a quadratic form over the inverse of the matrix regularized by that lambda. The important properties of this is one, that it can be, the sum of these scores can be bounded as a function of lambda and as a function of the matrix A, which is important because the sum of the scores, remember I'm sampling each row independently with these scores, the sum of these scores is my expected sample size. So if I want a fast algorithm, I'm going to need some way to bound the sum of these scores. The larger lambda is the smaller the sum becomes. When lambda is 0, this is, for example, when I need to do preconditioning or approximate system solves. The sum of the scores is at most the rank of my matrix. So as long as I select the number of rows equal to the rank of my matrix, I get this thing with additive error lambda equals 0. For low rank approximation, you can do things that are a lot stronger. If you appropriately set lambda, and I won't go into the details here, you can show that the sum of these scores is less than, or like, for example, 2k, where you're looking for a rank k approximation. This means that when I sample from my matrix, in expectation, I get 2k rows, meaning I get something like usually order k rows. I have this small matrix. I can perform an SVD on this matrix, which is reasonably inexpensive. It costs me maybe like d times k squared times. So this is a lot faster than doing an SVD in the original matrix. And I can get a near optimal low rank approximation of my original matrix. So it's critical that we're able to bound, we have good bounds on the sum of these scores because that's going to be our sample size.
So how is this related to Gaussian mixtures or k-means? Because a lot of this math looks like you're clustering the rows.
Yeah, if you have cluster structure in your data, it will sort of appear also in these leverage scores naturally. What you'll tend to have is that the leverage, say the points are really well clustered, then the leverage score of a row will be roughly like 1 over the size of the cluster that it's in, if they're really well clustered. And then as it's sort of a continuous, it will continuously interpolate as the data becomes less well clustered. Yeah. So this is one nice thing is this isn't so far from, it's also really closely related to DPPs, like determinantal point processes. Like the marginal distributions of DPPs, for example, are like the appropriately defined leverage scores. So it's not so far what people do in practice, but it's sort of a cleaner, can give you some cleaner guarantees when you sample. Okay. Yeah.
For low rank approximation, is there any way to make it k times 1 plus epsilon instead of like a constant times k?
No, not really. So it depends sort of what if you're looking for, here I'm hiding epsilon factors really. So I would actually say I'm looking for a constant factor in optimal low rank approximation. Mm-hmm. If I want to get, say, something within 0.1 of the optimal, you can prove that I better select, I need to at least look at like 10 rows, 10 times k rows of my matrix. So you'll get. So
I'm wondering if like the budget is only like an epsilon % of k, like if that's the number of rows I can select any way to get a 1 over epsilon approximation or something.
I'm not really sure. I don't know that you could do that. Definitely though, there's ways to run these algorithms. Like I'll talk later about kernel approximation where I give a budget on how much I want to sample and I sample under that. But typically the type of guarantees you get is I give you a sample of you can only sample k rows, you better only sample k rows, but then you maybe get an approximation bound which is matching the best k over 2 approximation, rank k over 2. Yeah, okay. Things like that. You have like trade-off there. All right. Okay, so what have we accomplished so far? We basically tried to take these problems that we care about, this linear system solving and low rank approximation, and write them as a simple guarantee. And this has let us get a really nice sampling distribution, this leverage score distribution that we can prove gives good approximation if we take enough samples. And we also have like an explicit data-dependent formula for this distribution, so this is great. We actually have the distribution in hand. We've removed a lot of the ad hocness from sampling for these problems. What's the problem is sort of, if you look at the form of this thing, it's glaring, is that I have to solve a linear system just to compute one of these probabilities. And I'm trying to accelerate these sort of methods. So solving this linear system is generally going to be pretty much as hard as the original problem I'm trying to solve, and we need to get around this. And this is a major contribution of our work. What we basically show is that we can efficiently bootstrap these leverage scores from uniform sampling. So I sort of knocked on uniform sampling earlier. I said it often cannot represent your matrix very well, but we can actually use it really powerfully for approximating leverage scores. Specifically, what I can do is I have my matrix. I want to compute leverage scores so that I can sample my matrix accurately. What I do is I first uniform sample half the rows in the matrix, and then I'm going to approximate leverage scores in this really simple way. If my row is in my sample, so if my row AI is in the sample of 1/2, this will happen half the time, then I'm just going to compute the leverage score in the smaller matrix, A bar. If my row is not in my matrix, what I'm going to do is I'm going to append it to the smaller matrix. I'm going to sort of pretend that I sampled it, and I'm going to compute the leverage score in this larger matrix, A bar, with the row appended. So I'm just going to approximate the leverage scores by cutting my matrix in half and then basically computing leverage scores in this smaller matrix, and hope that these things actually will approximate my original scores. And this is what we're going to show. We're going to show that overall, these approximate leverage scores are good approximations to the true leverage scores. Yeah.
Good enough that you can iterate this problem.
Yeah, so this will be the next slide, actually, yeah.
Wait, so second kind of thing you can do efficiently, you don't need to recompute it for every row you append?
This thing?
Yeah.
Yeah, in the end, what this will, I'll show you, but it's going to be a rank 1 update. We don't, first of all, yeah, it will be a rank 1 update to the inverse, so you can do that efficiently. Actually, what you can do is something even simpler, where you just compute the leverage score in this matrix, and you use the minimum of that leverage score in 1, the probability 1. So you can actually use an even simpler algorithm. You don't need to actually compute this out. Yeah. Okay, so why is this enough? So because you can iterate this process. So I want to compute the leverage scores in this matrix A bar. This requires computing some linear system, computing some like quadratic form over the inverse of A bar, which is half the size of my original matrix, but it's still pretty big, plus maybe a rank 1 perturbation, which I could deal with efficiently in a number of ways. But the problem is A bar is still too big. So what I'm going to do is I'm just going to recursively approximate A bar using leverage score sampling. Okay, so what does that look like? I start with my original matrix. I cut it in half to get A bar 1. Call that my first uniform sample. This is still too big to work with, so I cut it in half again to get A bar 2. I keep cutting it in half until I finally get to a matrix that I can actually work with. Note that this is just a uniform sample of my matrix, and maybe I stop when I can fit in memory, I stop when it has 1 row, whatever. And then what I do is, say I went down two levels, I use A bar 2 to approximate the leverage scores for A bar 1. A bar 2 is just a uniform sample of A bar 1. By my claim on the previous slide, I can do a good job approximating its leverage scores. I can then sample from A bar 1 to get a good approximation to A bar 1. And then what I can show is that this approximation can be used to approximate the leverage scores of A itself. A bar 1 could be used to approximate these leverage scores. It's not very hard to show that A tilde 1 can also approximate these leverage scores. And so finally, I work my way up to the top level of the computation, and I compute the leverage scores reasonably accurately. Okay, so that's the entire algorithm. The key is just proving that uniform sampling, if I uniform sample in half, this computes leverage scores. That's all we need to prove to get this thing to work. Okay, so this is what we need to show. We need to show that our approximate leverage scores, which we got from uniform sampling, are good approximations. And to do this, we actually only need 2 really natural properties of the leverage scores. One, we need that they're bounded by something. So for linear systems, in that case, they're bounded by the rank of the matrix. When you appropriately set lambda for low rank approximation, they're bounded by some universal upper bound 2k, where k is the rank of the approximation you care about. It's natural that they're bounded. They better be bounded, or else, because we're sampling by them, so if they're not bounded, then we don't know how big our sample size is going to be. So we use that they're bounded, and that they're monotonic, which just means that if I remove rows from my matrix, the leverage scores of the remaining rows only go up. And this is a very natural property for an importance sampling metric. A row can only get more important as other rows leave. Okay, so how can we use these to prove that these approximate leverage scores are good? The first claim is that my approximate leverage scores are only larger than my true leverage scores. So this means I'm only going to sample every row in my final process. I'm going to sample every row with some slightly higher probability than I should have. But this is fine. I'm only going to do a better approximation if I sample more rows. How do I get this? Well, this follows immediately by monotonicity. So in the first case, I'm just computing the leverage score against A bar. That contains half the rows of my matrix. The leverage scores of the remaining rows have only increased over their original value. So I over-approximate in that case. And same within the second case. I'm looking at A bar union AI. This is still a subset of my matrix. The importance of AI in this subset is only more important than its importance in the whole matrix. So I have over-approximations to the leverage scores. And then what I need to show is that the expected sum of the leverage scores, remember that the sum of the true leverage scores was something like 2K. I need to show that the expected sum of these approximate leverage scores aren't that much larger. So my sample size is roughly the same size. So they over-approximate my sampling probabilities, but not by so much. And this is all I need to get a fast algorithm. I'm not going to show you the proof of this, but it's really easy to prove. You basically, and so this is what it gives you. You basically use an averaging argument. You show that the average leverage score in A bar union AI is not too large, and then you sum up these expectations and you show that this expectation isn't too large. So it's actually super easy to prove this. You only need the monotonicity property and this boundedness property. Actually, I don't think you need the monotonicity property for that one. Okay, so that's it. So what's the upshot? We show that uniform sampling can be, we define some nice importance measure, and we show that it can be well approximated with uniform sampling. Yeah.
So in this big O, so when you iterate that, so you don't have a uniform constant that's valid throughout all the iterations, or you do. So I'm wondering so because you're going to go from, n to n, 2 and over 4 and so on. And is this big O uniform in all these iterations, or this is just for the first iteration?
It is uniform. Well, so there's a little details I'm hiding under the rug, which is you need to set lambda, like say we're doing linear systems and lambda was 0. This would be, this value k would be like D. It would be rank of the matrix, okay? If lambda was 0. And always this would be bounded by something like 4 times the rank of the matrix, something like uniform for every single iteration. If the rank of your matrix happens to go down when you sample, then it might get a little bit better, but it's never going to be worse than the rank of the original matrix. In low rank approximation setting, it's bounded by some constant times the statistical dimension, or sort of the stable rank of the initial matrix. This thing is going to only again go down as you sample, so it is really bounded by some uniform. I mean, well, it's bounded by better and better things as you go down, but worst case by the top level.
You said these are increasing, so how could it go down? As you...
The leverage scores are increasing, but you're removing rows. So the sum of the leverage scores is actually only going down. Yeah. Or staying the same, I mean, yeah. Okay. Okay, so this is the upshot is we use uniform sampling to approximate these leverage scores. These leverage scores give approximation for a lot of problems. It gives us a fast, generic importance sampling algorithm for a lot of linear algebraic problems. Yeah.
So what is the quality of the approximation? What is the difference between lambda and lambda?
So you can't actually bound, so you can't actually say that lambda tilde, for example, is within a constant factor of every, you can't actually say that like tau tilde is within a constant factor of tau for every single I. In some cases, for example, like tau I might be 0 and tau tilde might be some positive number, so you can't bound them. So you just have that in aggregate, you have a constant factor approximation. So the sum of the approximated ones are only a constant factor higher than the sum of the real ones. And you use these as a sampling probability, so it means you take a constant factor larger sample. So it's sort of, you pay it as a runtime cost, the difference.
So if I understand what Yuval is asking, and I actually also have the same question. So by sampling once, you lose in the constant. So initially you start with some being 2K, and then you lose constant factor. Why this constant doesn't aggregate over?
Because this is I only care about this for one level. So
I see, because
I sample once, I lose, but I don't really care about. I don't care. I'm going to ignore the leverage scores of the top level for a minute. I just want to approximate the leverage scores of the second level. So, yeah, you don't pay. You're not trying to approximate the leverage scores of the top level with, for example, the third level. You first sample this. You first sample A1, and you get some approximation to it. Say you get like a constant factor spectral approximation, a 10 factor. Then what the constant's going to blow up by from going from A1 to A is something like 10 times 2 or something. And then you fix this in every single iteration so it doesn't blow up.
I see.
If that makes sense.
I see. Well, I'll need to think.
Yeah. But yeah, things, roughly speaking, things don't balloon on
It
themselves.
sounds too good to be true, but I'm sure it's.
It's because you can always pay for, if you have approximate scores, you can always sort of correct for this by just oversampling by a constant factor, and now you have just as good of approximation as you would have gotten. So it's as if the rest of the recursion didn't matter at all. And now you just look at one level, and you complete that level, and you keep going. Okay. So the upshot is these fast generic importance sampling algorithms. You can get nice asymptotic runtimes. You can get things that basically match linear sketching methods or stochastic gradient, where you're paying for sort of like order 1 times the number of non-zeros in your matrix plus some smaller term, like this dk squared term for low rank approximation. And it's really easy to adapt into streaming, online, and distributed settings because it's not, you can sort of easily sort of distribute your computation of these leverage scores and then merge them back together at the end. But more importantly than these exact runtimes is that you can apply these methods in contexts where previous approaches like traditional iterative methods or random sketching completely fail. So I'm going to give you an example of that for kernel methods. In kernel methods, basically, I am trying to learn some nonlinear relationship amongst my data. I do this by replacing my standard inner product with some nonlinear inner product, this kernel function kxi(xj). And maybe it's like the Gaussian kernel, which I showed up there. And this implicitly defines this n by n kernel matrix where every entry is the inner product between data point x and data point I and data point j. Now, even writing down this kernel matrix takes n squared time. I might not want to explicitly write it down, but even do like a single iteration of a linear system solver on this kernel matrix. Say I'm trying to solve regression in this kernel matrix. This takes n squared time. Or applying a single round of random projection or hashing, this also takes n squared time. So this is really expensive. Even if n is 200,000, if it's not even that big of a data set, I have 40 billion entries. It will typically be a dense matrix. It takes 300 gigabytes to store. This thing just becomes very unwieldy. Especially if I go up to like millions of data points, then suddenly this is just not possible to work with this kernel matrix. So basically, all implementations of kernel methods at large scale use low rank approximation. You always take your kernel and you approximate it by some product ZZ transpose where it has some limited number of columns. You can store this in a lot less space. You can do computation a lot more efficiently. You basically need to do this, and you get some sort of linear and n runtime, which is important. And there's a lot of methods for computing kernel approximations in linear times. Things based on incomplete Cholesky factorization. This NYSTRÖM method is especially popular. There's this well-known technique called random Fourier feature sampling, which can be viewed as giving a low-rank approximation of your matrix. All these things run in roughly linear and n time. But that means that they're, for example, not computing every entry of the kernel matrix. And they have to pay for this. In the end, they never give error that's comparable. So ideally, I'd want the best rank S approximation to my kernel matrix. Computing this would be super expensive. If I wanted to do it even using an iterative method, even if my iterative method completed in one iteration, it would take n squared time. So these things are doing something much more limited to that, and they're never getting approximation in terms of this best rank S approximation. What we can show with leverage square sampling is we can actually close this gap, sort of surprisingly. We show that you can actually get a linear time method that gives a near optimal low rank approximation in sort of the sense that you want, which is this. We start with this basic thing called NYSTRÖM.
What does linear
Yeah.
mean? Linear in what exactly?
So by linear time, I mean linear in n. And it will be
n times dimension of these vectors that you use to compute.
Yeah, okay, yeah. So yeah, I'll explain that. I'll explain exactly what I mean. Yeah, so it'll be n times the number, that's times the size of your original input. Yeah. Yeah. Or sort of like n, yeah. Yeah, so we get a method that does this, and let me explain. So we base it, actually I'm sort of running low on time, so I'm gonna skip the exact basis of the method, but let me just tell you what the result is. Oh, actually no, fine, I'll explain it. So we base it off this thing called NYSTRÖM approximation, which is basically like you sample some landmark data points from your data set and you form some approximation based off this sample. You can view this as basically sampling some points in kernel space. So a big way that you work with kernel methods is that you write the kernel as an inner product between vectors in some higher dimensional space. Sometimes an infinite dimensional space, so I'm being really informal here, but think about these just as high dimensional vectors. I sample points in this space and I project the rest of my points to them, and that's how I approximate my kernel matrix. What we can show is that if you sample these landmark points with their ridge leverage scores in kernel space, and you sample something like S over epsilon landmarks, then you can get an approximation not of the kernel matrix K, but of this like kernelized data set where every row is one of your kernelized data points. You can get a near optimal approximation to this. So basically the approximation produced by NYSTRÖM is within 1 plus epsilon of the optimal low rank approximation of this matrix. In your runtime is linear in n and quadratic in S, where it's linear in n in the number of kernel evaluations you have to compute. And then the additional computation you need is linear n and quadratic in S. And it doesn't compute the entire kernel matrix K. We also get bounds for a bunch of other problems basically by going through these spectral guarantees. And this closes a big gap between linear time methods, which are basically the only thing you can run in practice, and actually like getting some sort of nice near optimal approximation bound. And practically speaking, it works really well. So I've plotted runtimes here. The important part is that where this blue line, we compare to these other linear time methods that don't give like a near optimal approximation to the kernel. And we're way faster than quadratic time, which essentially just doesn't scale. And then our approximation error, it's somewhere in between these methods, but it's going down much faster. A lot of the times these other methods sort of stagnate once you get to a certain number of samples. Our error is actually going down much, much faster and much closer to what you get with the random with this slow method, which is in this case random projection.
So your algorithm is black line, right?
No, our algorithm is blue line. So black line is like if you took your kernel matrix and applied a random projection, which actually is really expensive because you have to compute the kernel matrix. Yeah. So we don't do as well as that, but we do, much better than the other ones.
Being 2000 sounds a little bit.
Yes. Well, so the thing is that I can't compute. It's hard to compute these approximation errors. It requires computing the spectral arm of a super large matrix. So the reason this is small is because it's actually on pretty small. These matrices are not very large. It just goes to show scaling. Yeah. Okay. I guess I'm a little low on time, so let me just. I'll briefly summarize an even more surprising result you can get, which comes out of these kernel methods, which is that I give you any PSD, and this is again using these ridge leverage score sampling techniques. I give you any PSD matrix. I can output a near optimal low rank approximation, and the runtime is something like nk squared over some polynomial in epsilon. Note that my matrix, I have no assumptions on this matrix. So it could be dense, it could have n squared entries, it could have terrible condition number, it could be very incoherent. Yet I don't need to read this matrix and I can still get a near optimal low rank approximation to it. And this is just by bootstrapping this sort of kernel algorithm. We factor the PSD matrix as its square root times itself. If we applied the kernel approximation algorithm, you can work through our bounds and you'd see that we'd approximate the square root of this matrix, which isn't the same as approximating the matrix itself. But we show is that you can do something better. You can basically sample rows and columns of the matrix by the leverage scores of this square root. You can do it efficiently, and you can get down to this core of the matrix, which contains very few rows and columns. And from this, you can extract a near optimal rank approximation. The details don't really matter, but it's sort of, I thought that this was surprising. The only structural property we exploit from the matrix is that it's positive semi-definite, and then we don't need to read the whole matrix, and we can get a near optimal rank approximation.
Which epsilon would you typically want to apply this? Because one over epsilon to the 4.
Yeah, so this is like, first of all, this is like our bound. I don't know that this is actually the right thing, but it probably is at least 1 over epsilon. We have a lower bound of 1 over epsilon, and it probably at least 1 over epsilon squared. But even if, for example, you apply like a constant factor, often you're seeing your tail of your matrix fall off really quickly. So you're not looking for like really good epsilon. You just care about getting most of the mass of your matrix, and you're paying. Yeah. All right. So I guess I don't know. Does this end at half past or?
So I guess we had better quickly wrap up.
Yeah. So why don't I wrap up on the linear algebra section? I can take questions on it. And then if people want to stay, I can talk about the bio stuff, or I can just skip it. We can decide, okay? So, okay, this is a summary. What was the right way to select data points and features for linear algebraic computation? We considered simple, important sampling strategies. We defined like a very clear spectral approximation goal, and this let us define very clear probabilities. We then made this algorithmic and efficient by bootstrapping uniform sampling, and we're getting some pretty powerful results for kernel methods and for PSD matrices, and hopefully we can get more powerful results in areas where other randomized methods don't really suffice. In this talk, I mostly talked about sampling, one-shot sampling. I have a big matrix and I want to approximate it once. But obviously you can use sampling in a lot of other ways. So the obvious one is as part of iterative methods. And understanding how you can use sampling, for example, to speed up like second order methods is a really big question. And a sort of alternative way of using it in linear algebra. You can use these methods, these iterative methods, to give fast algorithms, as I mentioned, for lots of linear algebraic problems. So it's a really interesting area to look at. And also, we've been interested recently in generalizing this work beyond basic linear algebraic problem, for example, to like sampling Fourier features. We've used this specifically for kernel approximation, but hopefully it can be used in other Fourier analysis and sampling for Fourier techniques, and maybe for other types of models. And the last thing I'll mention is that I've been talking this entire time about how important like randomness is and approximation in these algorithms that I'm showing you. We don't really actually understand I don't know that this is really true. So I'll tell you one fact, which is that any fast algorithm on a matrix, so basically anything that runs in faster than order n squared, n cubed time, or faster than fast matrix multiplication time, if you want to think about that, uses one of two techniques. Either it makes assumptions on the matrix. It assumes something like bounded condition number or bounded eigenvalue bounds. This is how you get classic iterative methods. Or it does what we're doing. It uses randomization. It pays these 1 over epsilon squared or 1 over epsilon to the 4th factors. All algorithms that I know of, except for doing something like computing the trace or something, for any non-trivial problem, they fall into one of these two paradigms. And we want to explain why this is. Like, is there anything else we can do? Do we really need to be using randomization and approximation in order to get around assumptions? Or are there some class of faster algorithms that we just don't know about yet? A really simple question, just as a thought, is like, it's not even known how to deterministically compute an approximation to the top singular value of a matrix without computing a full eigendecomposition. Is this really the best we can do? Can you prove that it should be the best we can do, or are we really stuck there? Okay, so I'll close on that, and then yeah, I can take general questions.
I mean, actually, I'd like to see if you could do 2 minutes of showing us cool pictures of ants and stuff. That would be.
Yeah, I can do that. Okay.
Just really quick, maybe.
You
don't want to see ants? I think everyone wants to see ants.
Okay, yeah, I know. Yeah, linear algebra is a lot more boring than ants, unfortunately. So, okay, let me try to I'll just tell you exactly the thing that we've studied. So, what we've been interested in is understanding. There's all these biological systems that are essentially running randomized algorithms. Ants essentially run like randomized algorithms, and not only do they run them, we know what they're running because biologists can probe their behavior and figure out how does this ant make this decision? What's the input that causes them to make this certain decision? But biologists don't really have a good way of analyzing and figuring out how all of these things fit together. So the process that we've been studying is basically there's these certain ants, these rock ants, that basically they have to do this process of when their nest becomes too small because their colony grew a lot, or when their nest is destroyed for some reason, they have to go find a new nest. And they have to do this in a distributed way. So there's no central controller to say, look for a new nest and move to it. So the algorithm that they run is first some scout agents, some small subset of the population. They notice that their nest is messed up for whatever reason, and they start going looking for new nest sites. They assess these nest sites, and they can do this. Each individual ant is complex enough to actually assess the quality of a nest site. They can roughly measure its size. They can measure how much light is in there, so sort of how protected it is from the elements and things like this. So they get some sort of really coarse approximation to its quality. Both of these things are random. They're not like doing some sort of grid search or something. They're just randomly walking around, and then when they see a nest site, they assess its quality. And this triggers something. If it's above a certain threshold, they make a decision. This decision is that they decide to recruit other scouts to try to assess this nest quality. So if the nest is good enough, they go back to the home nest. They randomly walk around. They randomly bump into another ant, and then they try to recruit it to actually do its own assessment, its own independent assessment of the nest. It does its own random assessment. They keep doing this process. Eventually, it builds up to a sort of quorum threshold of ants that actually think this new nest is like a good nest. And then this is also a random process, that's why I highlighted it. What they then do is they decide on this nest. So if there's enough scouts that are somehow recruiting to this nest, they can actually sense this. It triggers something in their mind where they say, this is our new home. And then what they do is they initiate a decision-making process. What they do is they actually move the entire rest of the colony over to this new nest site. And this is sort of necessary because a lot of the agents in the colony are immobile. So the queen is immobile, the brood is immobile. There's a lot of ants that for whatever reason, ununderstood, they just sit around and don't do anything. What they do is they literally go back to the nest, they pick up the other ants and they just carry them to this new nest site. And this is how they move. And so this is like, yeah, right, exactly. Well, they're trying to analyze the algorithm, yeah. So this is like, it's actually a super well understood algorithm. Biologists like know exactly what they're doing. They can test things. Like for example, they can test if they can prevent the ants from reaching quorum threshold. They literally do things like put skirts around the ants, little wire skirts, so that they can't interact with other ants. And then they notice that, for example, they'll never reach quorum threshold because they can never detect when they're bumping into other ants and things like that. So they can really test what they're doing. The question becomes analyze what they're doing. Why is it working with good probability for them? And also, like, why are they doing it? How is the quorum threshold decided? So should the quorum threshold increase as colony size increases, or should it be independent of the size of the colony? Should it have something to do with the number of potential nest sites in the area? Do they adapt it, or is it just fixed? Answering all these questions is really interesting questions for biologists, and they're questions that we have the tools to solve. So
how do you objectively evaluate whether they found a good nest?
So usually it's in a lab setting, and okay, there's some parameters you have to decide what makes a good nest, but usually you set up a nest in a lab setting that, for example, some nests will have a closed top, which is good for them because it's more protected. Some will have no top at all. Some will have a small entrance, which is easy to defend. Some will have a large entrance. So you can sort of, some vague understanding of what good means. Yeah.
And what happens if two quorums form some at the same time?
Yeah, so this is sort of the fail case. I mean, one fail case is getting a bad nest. The fail case that happens more often, at least in lab situations, but it doesn't seem to happen for whatever reason in nature, is they split. The queen can only go to one of those colonies, so the other colony will die out unless they move. Usually what happens is they do move. So usually what happens is if the nests are close enough, they also have a process where they notice that there's two nests and then they eventually recombine, but it often takes a long time.
We're trying to take the queen.
Yeah, you don't have like a fight over that because I don't think they're coordinated enough to do that. But like in general, yeah, if you end up in a nest without the queen, then that subset of the population will just basically, they'll die off. I mean, not the individual ants, but yeah.
So you mentioned that they do random exploration. Is there any good understanding how high quality the random number generators are? Like, can you use them to?
I don't. So no. I mean,
like, did you use random in the precise sense, or it's random?
I use it in precise sense. Okay, this is the only way that I've seen this studied. Well, as I'll get to on the next slide. Let me answer that in 1 second. So we have some work trying to understand this quorum threshold strategies and when it's effective and why it's useful. And it has close connections, not surprisingly, with like distributed consensus protocols. And then we also have some work on zooming in on one primitive that these ants use, which is estimating population density. This is what they use to estimate quorum threshold. So there's a high density in a nest. This means that probably more scouts are trying to recruit there, and then they're more likely to be in quorum, and that it's a good time to move to that nest. And so how do they estimate population density? Well, they walk around randomly, and they count the number of times that they bump into another ant. The more times they bump into another ant, the higher the density, the less times, the lower the density, okay? And what we do is we basically analyze this process and give some sort of analysis about why they're able to analyze density and why this suffices for something like quorum thresholds. Now, our analysis assumes that they're literally random walking agents, which is certainly not true. What you can do to sort of try to at least test whether the analysis, so what some people have done, at least to test to some degree whether the analysis holds, although you would need to do more work, is, for example, take videos of these ants, label them individually and count the number of collisions you have between different ants. And then look at the distributions, the moments of this distribution, how many times you collide with other ants. And then you can say, is this about what you'd expect if they were walking around uniformly at random? So like some people have actually done work on this, like following up on our work, and they do show that it is close to what you'd expect from a uniform distribution.
Zero approximation, this random assumption is decent.
Yes, yeah, exactly. So at least to some degree, this random assumption is decent. And you could eventually do other things. So you can try to test it, like, to some degree. I think that's it, actually. There's close connections with social, like, so estimating population density is not so different from estimating area, the area that you're spread out over, and there's close connections with estimating the size of social networks via sampling. So we show some connections there. So with that, I'll wrap up. I can take questions on the ants or also on the linear algebra or whatever. Yeah.
Do you do any kind of intervention during the process? Like you deliberately change the potential nest, or you deliberately split the ants?
Yeah. So Yeah, so this is the one example I was saying was with these metal skirts. What they'll do is they'll let the ants run the process mostly, and then they'll somehow restrict their movement or restrict so that you can see whether or not they end up making. They would have made a decision, and you stop them from making the decision.
So you stop them after they've already started investigating a nest, or at the very beginning?
You stop them in this experiment that I'm talking about. You actually stop them after they've already investigated and also recruited some other ants to that nest and stuff. There's also there's a lot of like really cool. I mean, I don't actually I don't design these experiments. This is like we're working with people that design these experiments, but they do a lot of like physical things. Like for example, there's a lot of studying in how they can cooperatively transport large pieces of food, which is something they do a lot. And there you can put 4 sensors on this fake food. You can put 4 sensors, and you can try to figure out exactly what they're doing. Yeah. Mm.
So I had a question on the previous part. So you said many of your algorithms for sampling, you could they can also run the distributed model. So what exactly is the distributed model?
Yeah. So
because like I think like even graph specification and things, I don't know whether they can be solved in distributed settings.
Well, so the model, I'm just vaguely saying that I'm talking about a model where I have a number of servers, say they're well connected to each other, and each of them holds some subset of my data.
Yeah.
It's really natural to distribute our algorithm to these sorts of models because you can compute leverage scores separately on the data sets. And by this nice monotonicity property, you can really easily merge your samples together. And you can sort of so I compute leverage scores separately on the different subsets of my data. I sample it down to get some sort of small subset. And then I can recombine. When I recombine, my leverage scores only decrease, and then I can sample them out, basically. So I'm not talking about a model, for example, where every single data point is its own server or something like this.
Right.
Yeah.
I mean, you work with the party, so they have very specific.
Yeah. I'm not talking about those sorts of models. Yeah.
Okay.
So people that I work
Because
with,
I think this graph specification in the distributed model is quite an.
I think this is now like known. There's some recent progress on this using like random spanner type methods, and then But either way, yeah, it is important questions, but I'm not thinking about those sorts of models really. Yeah.
I guess let's maybe take the rest of the questions offline and thank the speaker again.